Section 10.1 is about exponential functions. Here you see an exponential function. The base, if you notice, is a constant while the exponent is a variable, and that makes up an exponential function. I don't want you to confuse this with something that we've been dealing with, which is y equals x squared. That's a polynomial function, and we've been using that for a long time. But now I want you to notice the exponent includes the variable while the base does not, and that makes a new kind of function called an exponential function. So let's take a moment to examine our function y equals 2 to the x. We'll get some ordered pairs in this function, and we'll sketch a graph and see what we can learn about it. I'm going to start with -3, and I'm going to go all the way to 3, and that should give us a good look at what the function does when you plug in values. So if I plug a -3 in for x, I'm going to get y equals 2 to the -3rd. Remember, negative exponents can be turned positive by moving them to the bottom of the fraction. So that becomes 1 over 2 to the 3rd, which is 1 over 8. Plug that into a calculator and you get 0.125, which is a very small decimal number. And we're going to keep going with that. So 2 to the -2nd is 1 over 2 squared, which is 1/4. So that's 0.25. Plugging in a -1, you get 2 to the -1st, which is 1 over 2 to the +1st, which is 1/2. Putting a 0 in, you get 2 to the 0, which is just a 1. So I'm going to take these ordered pairs and I'm going to graph them and try to get an idea of what the sketch could look like. So here are the ordered pairs that I've gotten, and I'm going to draw a sketch of this. The line is really small here, but then it begins to increase as we go along, and it's going to go up like this forever, and here it's going to go to the left forever. And that's what an exponential function looks like when you graph it. Notice these numbers, as the x goes to the left, will continue to get smaller and smaller and smaller, but they will never actually hit 0. So this line is going to get closer to 0, but it will never actually hit it. And then this line is going to go off forever and eventually become every y value that you can think of. So we're asked to find the domain and the range. So what are the x values that we could plug in here? Well, we can plug any x value we want. So the domain is all the real numbers. And then the range is which y values. Well, we're never going to get below 0, but we're going to go above 0 forever. So that would be all the positive numbers. On this slide, I just wanted to show you another set of exponential functions. The one on the right here in the red is y equals 3 to the x, and the one on the left here in the purple is y equals 1/3 to the x. So you can see that when you have the base and you flip it, it takes the graph of the function and it flips it over the y-axis. It's symmetrical with respect to the y-axis. And so I just wanted to show this to you so you could see a graphical representation of a couple other exponential functions. So here you find all the general information about exponential functions. They have to be continuous or one-to-one. The domain is all the real numbers. The x-axis is an asymptote, which means it's going to get close to the x-axis, increasingly closer, but it's never actually going to get there, never actually going to get to 0. Number 4, the range is all the positive numbers or all the negative numbers. Now I want to show you that you could have a parabola that goes like this. It gets close to the x-axis there but goes down, and that would be an example of where the range values would be all the negative numbers. So I just wanted to show you that graphically. You can also find a y-intercept using the 0 for the x. You'll get a y-intercept, and then the graphs look like this, but if you reflect the base, or if you use the reciprocal of the base, you reflect the graph over the y-axis as I showed you on the last slide. So here's the key concept. It says that if you have a base with a variable as the exponent, it's an exponential function, and one that goes up and to the right, as you see this one over here, that's going to be a model that scientists use for exponential growth, how things grow. Likewise, if you use the one on the left, which is the one on this side, that's going to represent a model of exponential decay. In that case, the graph goes up and to the left. and that happens when your base is between 0 and 1. So here we're given three exponential functions, and we have to determine if they're exponential growth functions or if they're exponential decay functions. Well, this first one, the base is 0.7, which means it's between 0 and 1. Therefore, this is a function that represents decay because the base is between 0 and 1. In this one, the base is greater than 1, so this is exponential growth. Even though it does have a 1/2, the base with the variable is greater than 1. So that's going to be a growth function. And this one, 4/3 is a fraction, but it is greater than 1, so this represents exponential growth. Okay, so here's an example of exponential decay in which we have a number of farms in a certain year, and then by another year we have a lower number of farms. So you see the number of farms is decreasing, and we're going to have to write an exponential function to model this relationship and then try to use that to predict something that's going to happen later. Well, if you notice, we start in 1983, we have 102,000 farms, which means the initial value is 102,000. Now that's your A. Your A value is the initial value. It's the value that your relationship is going to start at. It is the value of the y-intercept. If I have 102,000 for A, my x value is a 0 right there, which means no time has passed, and so that's my initial value or my y-intercept. So I know that my A is 102,000. What I have to find is the B, because if I know the A and the B, then I can write my exponential function. Well, I have a lot of information here that I can use to help me find my B. If I go from 1983 to 1998, I see that that is 15 years. So over the course of a 15-year span, I decrease all the way down to 80,000 farms. So since x is the number of years since 1983, that means my x value is going to be 15. And I don't know my b value because that's what I'm actually trying to find. I do know my A value is 102,000, which means that's my initial value, and then after 15 years, I end up getting to 80,000 farms. So I know that I can plug 80,000 in for y, because that's how many farms I get after 15 years. And I can use this equation to help me solve for the b. So we'll divide by 102,000, cross off zeros, so this will reduce to 40 over 51 equals b to the 15th power. And to get rid of a 15th power, we use the 15th root. So these will cancel. So b is going to equal whatever the 15th root of 40 over 51 is. So you plug that into a calculator. And you're going to get about 0.98. So that's what we'll call our b value. So I have my b, I have my initial value, which is my a, so now I can write my exponential function. Y equals 102,000 times 0.98 to the x power. And x represents the number of years since 1983. So there's my exponential function. So now I go down here and I say, suppose the number of farms in Minnesota continues to decline at the same rate. Estimate the farms in 2010. So since 2010 is going to be 27 years from 1983, then I'm going to say my x value will be 27 here, and I'll plug it into this formula. Get a calculator, and you get an approximation of 59,115, and we'll label that farms in 2010. Here you have a couple problems that deal with exponents, and just a reminder of how to do the different rules with exponents. When you multiply bases that are the same, you're going to add exponents. So in this case, we will simplify to something like this. When you take a power to a power, you multiply exponents. So you're going to say square root of 2 times square root of 3. Now, unlike the last one, that can simplify, and you can do square root of 6. So you can simplify it that way. So now we have another key concept that deals with the property of equality for exponential functions. If you have two exponential functions and they're equal, their bases are the same. Well, if their bases are the same, then you can say their exponents are equal. We're going to use that to help us solve equations that have exponents with variables in them. So if you go down here and I say 3 to the 2n plus 1 equals 81, well, if I could somehow get these bases to be the same, then I could set the exponents equal to each other. So can I write the number 81 as 3 to some power? And the answer is yes. 81 is 3 to the 4th power. So because of my property, the bases are equal, therefore I can say that the exponents have to be equal. And so what I've done is I've created a whole brand new equation that I can use to solve for n. So subtract 1, divide by 2, and we can see that n equals a value 3/2. I'm only able to do this if I can somehow get the bases to be the same so that I can set the exponents equal to each other. So over here, I have two exponential functions, but I don't have the bases the same. I can't get the number 8 to be written like a 4, but I can get both of these numbers to get written with a 2, because 4 would be 2 squared to the 2x, and 8 would be 2 cubed to the x minus 1. Now when you take a power to power, you multiply, so this is really 2 to the 4x equals 2 to the 3x minus 3 if I distribute the 3 to those. Now the bases are the same, and I can set these two exponents equal to each other and solve. So x equals -3. Our last slide here is another key concept which takes the last one and just expands on it a little bit. It adds an inequality symbol, and that basically says if you have two bases that are the same and there's an inequality between them, that inequality will stay there, but you can only deal with the exponent. So if you have two bases of 5s, you can say the x is less than the 4 and then rewrite a separate inequality that you can then solve. So again, it's all about making the bases the same. So if I go down here and I look at 4 to the 3p minus 1, I would love to turn this 1 over 256 into something to the 4th power. Well, 256 is 4 to the 4th power. So we could say that this is 1 over 4 to the 4th power, but I would like this to just be a 4, not a 1 over 4. So I could rewrite it a further step by making this 4 to the -4th power. And now I have bases that are the same, so I can forget about the bases for a while and just say 3p minus 1 is greater than -4. And now you can solve this like you normally would. And so you end up with p is greater than -1.